Hello and welcome to this video lesson on gas equilibria with specification reference 3.1.10. In this lesson on gas equilibria, we're going to do two things. We're going to state what is meant by partial pressure. We're going to understand that. And then we're going to apply the equilibrium law to gaseous equilibria. Before we were dealing with aqueous equilibria. By before I mean in year 12. So partial pressure. First of all, let's get our heads together and understand a gaseous equilibria. We will have met this equilibrium reaction here, where you've got hydrogen molecules and iodine molecules, both gaseous, and they're going to be in equilibrium with hydrogen iodide gas. So you'll remember that the forward reaction will be making hydrogen iodide. Like that. And at the same time, at the same time as this, where hydrogen molecules and iodine molecules are combining to make hydrogen iodide molecules, at the same time the backward reaction is happening. So you've got two hydrogen iodide molecules decomposing back into hydrogen gas and iodine gas. All right, so that's what's happening, and both of those reactions are happening simultaneously. And depending on the conditions, there'll be so much hydrogen, so much iodine, and another amount of hydrogen iodide. So let's imagine this reaction, this equilibrium happening in a sealed container like this. And so we're going to have hydrogen molecules. Let's make them red. And we're going to have iodine molecules. Well, we have to make them purple, don't we? Right, so let's have a few of those. And let's have a few more iodine, hydrogens. Like that. And you're also going to have some hydrogen iodides. So we'll make the hydrogen iodides mixture of red and purple, like this. Okay, so we've got three different molecules in this sealed container, and the equilibrium is as we've just described. And so in the container, these molecules are bashing against the container's walls like that and exerting a pressure as they move and collide with the walls. And so the hydrogen molecules, the H2 molecules, they're bashing against the walls and they're creating a pressure, as are the iodine molecules, as are the hydrogen iodide molecules. So what we can say is that the total pressure is the sum of the partial pressures. So the partial pressure, let's give that a, let's change colour. Let's go back to, not use green, let's use green. So the partial pressure of the hydrogen plus the partial pressure of the iodine plus the partial pressure of the hydrogen iodide is equal to the total pressure. And so each of the partial pressures, each of the pressures of the hydrogen, iodine and hydrogen iodide are known as partial pressures. And the sum of each one in an equilibrium is the total pressure. So let's illustrate this concept with a worked example. Here we are. Okay, let's illustrate this concept with a worked example. Here we have 3 moles of the gas phosphorus pentachloride, and when we heat it, it decomposes into phosphorus trichloride and chlorine according to that equilibrium reaction. So it's an equilibrium reaction, so we know that it doesn't all decompose into phosphorus trichloride and chlorine. Some of it remains as phosphorus pentachloride as it's recreated by the two products there. Okay, we're told we've got a sealed vessel at a temperature, doesn't matter what the temperature is, I think, and we're told the equilibrium mixture contains chlorine with a partial pressure of 263 kilopascals, but the total pressure is 714 kilopascals. And what it wants you to work out is the partial pressure of phosphorus pentachloride, that amount of phosphorus pentachloride that is left after some of it has decomposed into trichloride and chlorine. Okay, so let's just illustrate what we mean, what the question is all on about. So let's draw a sealed vessel, and this is, contains 3 moles of, let's draw 3 molecules of the black circle. Let's make the black circle phosphorus pentachloride. So at the start we've got 3 moles of phosphorus pentachloride, and then we leave that and it reaches equilibrium, and the same sealed vessel will contain all 3 different gases. So there'll be some phosphorus pentachloride, there'll be some phosphorus trichloride, and there'll be some chlorine as well. It doesn't matter about the numbers of molecules, we're just illustrating the fact that we've now got 3 different gases at equilibrium. So let's just write this down at equilibrium here. Okay, and at equilibrium we are told that the partial pressure of the chlorine is 263 kilopascals. And we're told the total pressure, and we know that the total pressure is the partial pressure of chlorine plus the partial pressure of phosphorus trichloride plus the partial pressure of phosphorus pentachloride. Okay, and the total pressure is 714. So we know 2 out of 4 of the variables. However, what we can also deduce from the question is that the same number of molecules of phosphorus trichloride are going to be made as the number of molecules of chlorine that are going to be made, right? Because the balanced equation shows us a 1-to-1 relationship in the equilibrium. So we can say that the partial pressure of the phosphorus trichloride is also 263 kilopascals. Therefore, let's just write down all that we know. The total pressure, 714 kilopascals, is equal to the partial pressure of chlorine. We know that that is 263, plus the partial pressure of phosphorus trichloride, which is also 263, and it's also going to be it's going to need to include the partial pressure of phosphorus pentachloride, which is what we don't know, and that's what the question is asking us for. Okay, so now it's easy to work out. So the partial pressure of phosphorus pentachloride is going to be 714 take 263 take 263 equals 188 kilopascals. Here's another concept you need to be familiar with. It's called mole fractions. It's quite easy, I think. And a mole fraction is just the fraction of gas that's in a mixture. So let's draw a little diagram here. We've got a sealed container containing, let's say it's got 1, 2, 3, 4, 5 moles of A, and let's say it's got 5 moles of B. Then the mole fraction of A is going to be 5/10, Right, so the mole fraction of A is the moles of A divided by the total number of moles, and mole fractions of B is going to be the moles of B divided by the total. And in this case, didn't we say it was 5/10 for both of them, like that. And we do have some equations to remember. So the mole fraction of a gas is the number of moles of that gas divided by the total number of moles in the mixture. That's what I've written down there. And the other equation for you to remember is that is relating partial pressure to the mole fractions. So the partial pressure of a gas in a mixture is the mole fraction of that gas times the total pressure of the mixture. So what we might do on the next slide is just do an example of the use of that second equation there. These two equations, by the way, you do need to remember. They won't be on your data sheet. I think they're quite intuitive as they are, so they shouldn't be too difficult to remember. But let's have a look at an example of partial pressure and mole fractions. Here's our worked example. We start off with 2 moles of phosphorus pentachloride. We heat that, sealed vessel, and some of that decomposes into phosphorus trichloride and chlorine. And we're told that at equilibrium we have 1.25 moles of chlorine. And the question is, what is the mole fraction of phosphorus pentachloride? Okay, so the first thing we should do is write down our equilibrium equation. So we're going to start off with phosphorus pentachloride in equilibrium with the two products it decomposes into, phosphorus trichloride and chlorine gas. Okay, so what I like to do is I like to write down starting moles. Starting moles of phosphorus pentachloride is 2.00, and we've got 0 moles of phosphorus trichloride, and we've got 0 moles of chlorine at the start. And at equilibrium, we are told that we have 1.25 moles of chlorine. So we can say 1.25 here, but we don't know yet how much phosphorus trichloride we've got, and we don't know how much phosphorus pentachloride we've got. So that's what we've got to work out. Now, from the balanced equation, we can see that there is a 1-to-1 relationship between phosphorus trichloride and chlorine. So we can say that we have got 1.25 moles of phosphorus trichloride as well at equilibrium. And we can also quickly work out how much moles of phosphorus pentachloride we must have at equilibrium, because 1.25 moles of it has decomposed into the two products. So 2.00 take 1.25 equals 0.75. So it's 0.75 moles of phosphorus pentachloride we have at equilibrium. Sometimes students struggle with the fact that we've now got more moles of products at equilibrium than we had before equilibrium. We started with 2, and you can see that now we've got total moles at equilibrium is our 0.75 plus our 1.25 of phosphorus trichloride plus our 1.25 of of chlorine. So the total moles are going to be 3.25 moles. 3.25 moles at equilibrium, but we had only 2 at the start. But that's of course because 1 mole of phosphorus pentachloride decomposes into 2 moles of products. Okay. But the question is asking us for the mole fraction of phosphorus pentachloride at equilibrium. So the mole fraction of phosphorus pentachloride is going to be the moles of phosphorus pentachloride, which is 0.75, divided by the total number of moles, which is 3.25. So our mole fraction turns out to be 0.231. To 3 significant figures because our data is given to us as 3 significant figures. QED. Here's another. Here we have a mixture of 8.02 grams. So notice grams, not moles, nitrogen, and 42 grams of oxygen. Here's the pressure mixture, 921 kilopascals, but it's asking us for the partial pressure of the oxygen. Okay, so in this mixture, sealed vessel, we have nitrogen here and oxygen as well. Okay, so let's first of all convert the grams into moles because grams are no good to us here in chemistry. So we're going to say moles of nitrogen is going to be our grams, 8.02, divided by our AR of nitrogen, which is 14 times 228, and our moles of oxygen is going to be our grams of oxygen, 2.42, divided by our AR of oxygen, which is 16 times 232. So this 8.02 divided by 28 works out at 0.286, and oxygen works out, moles of oxygen works out at 0.0756. So that's our mole, the moles of each one. So the total number of moles is just the 2 combined, 0.286 plus 0.0756 equals, let's call that 0.362 to 3 significant figures. Okay, but let's look back at the question, see what it's asking us for. It's given us the total pressure, 921, but it wants the partial pressure of the oxygen. So the partial pressure of the oxygen is going to be the mole fraction. The mole fraction of the oxygen, which is going to be 0.0756. That's moles of oxygen divided by total moles, 0.362, times the total pressure, 921, and that's going to come out at 192 kilopascals. QED. So we're going to move on to a new concept now, and it is the gas equilibrium constant, Kp. Now, you might remember from year 12 we had Kc, right? And Kp is just like Kc, right? It's an equilibrium constant, but for Kc it was with solutions and we had concentrations. And with Kp we've got gases and we've got partial pressures. Otherwise it's all pretty much the same. So let's have a look at the equation for it. So we've got an equilibrium here. We've got two reactant gases A and B, two product gases D and E. And what we can say is that Kp is going to be the partial pressure of the two products, right? So first of all, partial pressure of D, and it's to the power of the moles of D. All right, so you see that little d there appears as our exponent for the partial pressure of D, and that's multiplied by the same thing for E. Okay, so it's the partial pressure of E to the power of the number of moles of E in the balanced equation. Okay, so products on top, reactants on the bottom. So on the bottom we have the partial pressure of A to the power of the number of moles of A times the partial pressure of B to the power of the number of moles of B in the balanced equation. So that's how it is, very similar to Kc, except here we have gases and partial pressures instead of solutions and concentrations. So let's cement it with a worked example, shall we? So here we've got a question that requires us to calculate Kp for our favourite reaction of the moment. We're going to decompose phosphorus pentachloride, and as we know, it decomposes into phosphorus trichloride and chlorine. And we're told in the question that the partial pressure of the pentachloride is 188, trichloride is 263, and chlorine is also 263. Okay, so let's start off by writing down our equilibrium equation. So we're going to have phosphorus pentachloride in equilibrium with phosphorus trichloride and chlorine, all gas. Okay, so we're going to write down our expression now for Kp. So you remember products over reactants, so it's going to be partial pressure of phosphorus trichloride to the power, let's put the moles in there. Since they're ones, of course we don't write them, but it's 1, 1 and 1 there, of course. Right, so that's all to the power of that partial pressure to the power of 1 times our partial pressure of chlorine to the power of 1, all divided by our partial pressure. So be careful not to get mixed up as like I am with partial pressures in phosphorus. So we've got a partial pressure of phosphorus pentachloride also to the power of 1. So substituting in our numbers, we need to put first of all our 263 for phosphorus trichloride times our 263 for our chlorine divided by our 188 for our phosphorus pentachloride, and that all comes out at 368. But 368 what? What are the units? What are the units? We need the units, of course. Right, so in the same way we will write the units of each of our components of our equation. So we've got kilopascals, so another P, times kilopascals for the other product, and we've got kilopascals for phosphorus pentachloride. That's going to cancel with that, so our units are kilopascals, which we write in back there. So that's our answer there. And that completes this video lesson, apart from our little roundup. So gas equilibria. Do we know what is meant by partial pressure? I think so. We've done it. And have we covered off the equilibrium law have we applied it to gaseous equilibria? Yes, that's the formula for Kp. Equals all the partial products of the partial pressures of the products to the power of the number of moles in the balanced equation divided by the partial pressure of the reactants to the number of moles in the balanced equation. So I think we can give ourselves a tick for that as well. Hopefully you also found that clear. Let me know otherwise.